Rosen, Discrete Mathematics and its Application, Section 10.2 on graph terminology and special types of graphs. Here we discuss one special type of graph called a bipartite graph. And a bipartite graph, a graph is bipartite if its vertex set can be partitioned into two subsets such that every edge connects vertex 1 to a vertex in vertex 1 to a vertex in vertex set 2. In other words, there's no edges which connect two vertices in V1 or in V2. And an equivalent definition of a bipartite graph is where it is possible to color the vertices red or blue so that no two adjacent vertices have the same color. Here I have an example where we can show that G is bipartite, and we will start by coloring as many vertices as possible with one color. It'll be red. We start with A, and then we note that we can color B with red because it is not adjacent to A. And then I see that D is another vertex that is neither adjacent to A or B, and I can color it red. There's no vertices not adjacent to those two, but we can color all of them blue because they're not adjacent to each other. Now if I can color all the vertices of a graph with two colors such that no two colors are adjacent to each other, I have a bipartite graph. Notice on graph H, however, we will not be able to color that with only two colors, because if we color A red here, then F and B would have to be two different colors because they are adjacent to each other. So graph H is not bipartite because we cannot two color it. Another way that we can show bipartite nature of a graph, here's C6. We could two color this graph rather easily. Just go around red, blue, red, blue, red, blue. And or what we can do is pull the vertices that are not adjacent into their respective bipartitions. So if I label this graph as V1 and I go around the cycle, V1, V2, V3, V4, V5, V6, every other vertex will be in V1, and then every remaining vertex will be in V2. So that if I pull them apart visually into their regions V1 and V2, and I can see that they do not have edges between any two vertices in either of the bipartitions, and so it is bipartite. C3 is not bipartite. By similar reasoning as before, we couldn't two color it. It would require three colors to color these vertices so that no two colors are adjacent. But also, if we try to divide the vertex set into two non-empty sets, the one of the two must contain two vertices, and if we do that, then it's going to contain an edge, and therefore it cannot be a bipartition. Okay. Here's the definition of a complete bipartite graph. It has designation Km, N in the indices. And that is a bipartite graph that has a vertex set partitioned into two sets, V1 of size M and V2 of size N, such that there's an edge from every vertex in V1 to every vertex in V2. You can't add any more vertices to a complete bipartite graph and remain a bipartite graph. Here's four different types. K23, two vertices and three vertices, as many edges as possible and still be bipartite. K33 is a very important graph from a graph planarity standpoint. We'll see that in the later section. K35 and K26. And how many edges are there in a complete bipartite graph? Well, there's n edges for m vertices in set V1, so that means number of edges is equal to m times n. Okay. Here's a few more definitions to keep in mind for not just bipartite graphs, although we'll be back discussing those. The first one is if you have a graph G, which has got a vertex set and an edge set, a matching is a subset of the edge set so that no two edges in E are incident on the same vertex. Here I have a graph with 5 vertices and 7 edges. And a matching would be, I could just take one of those edges and that's a matching. Or I could take 2 of the edges and that's matching, but they have to have different vertices at their endpoints. A maximum matching is a matching with the largest possible number of edges. So earlier I had picked this vertex and that vertex from my graph above, but not vertex, edges, sorry. This edge and that edge, we'll call it edge 1 and edge 2. And that represents a maximum matching because it connects to 4 vertices, and there's no way I can add an additional edge that doesn't touch a vertex already contained in the matching. All right, now back to bipartite graphs. If I have a bipartite graph, G, vertex set E, edge, vertex set V, edge set E, and bipartition V1 and V2, as discussed earlier, if I have a matching, we say that it is a complete matching from V1 to V2 if and only if the size of the matching is the same as the size of the vertex set V1. In other words, every vertex in V1 is the endpoint of an edge in my matching. No vertex in V1 is left out. And we have a theorem that governs whether or not there is a complete matching from V1 to V2 in a bipartite graph. And it's known as Hall's marriage theorem. And it states that a bipartite graph with bipartition V1 and V2 has, oh, that's not very good, has a complete matching from V1 to V2 if and only if the cardinality of the neighborhood of A is greater than the cardinality of A for every subset A of V1. Okay, and this is known as Hall's matching condition. If the cardinality of the neighborhood of A is ever less than the cardinality of A, then we cannot find a complete matching. The proof uses strong induction as found in the textbook. It's quite intricate, and I recommend you read it and take a look at it. Let's apply it though. We use bipartite graphs to model many things, especially if we want to match elements of one set to elements of another set. Job assignments represent a good example. If you have vertices representing jobs and another set of vertices representing employees, the edges represent the jobs those employees are trained to do. And then a complete matching of, say, employees to jobs means every employee is given a unique job to them, or a complete matching of jobs to employees would mean that every job is being carried out. If there's an equal number of employees and jobs, then a complete matching connects every or includes every vertex. Here I have a complete match. Here I have a bipartite graph of employees related to jobs, and if I select all of these light blue ones, I see that I can find a complete matching that from the employees to jobs and also from jobs to employees, since the cardinalities of the two sets are equal. On the other hand, here we have a bipartite graph that represents another set of employees with different kinds of jobs that they're trained to do. And we will not be able to find a complete matching from the employees to the jobs because look at Washington and Ibarra as a subset of my employees, it has a cardinality of 2, but their neighborhood has a cardinality of 1. There's only one vertex in their neighborhood, and that violates Hall's matching condition, and therefore we will not be able to find a complete matching in this bipartite graph, V1 to V2 or V2 to V1 as well. And you can look for the subset of V2 that is cardinality greater than its neighborhood in V1. Another application is marriages. If you have groups of men and women and they are linked, if they are compatible as spouses, you might want to find the largest number of marriages in a uh, population of men and women. And that's what gave rise to the name Hall's marriage theorem. And that is our discussion of bipartite graphs and Hall's marriage theorem.